All right, AP Stat, this is your example 1 in your notes. I did this in class, but I just wanted you to have it on video in case you forgot how to do it, or in case you need to revisit listening to my voice about it. So I've got some data up here. We've got average heights of Kalama children, and we've got age in months and height in centimeters. And of course, age drives height. As you age, it increases your height when you're a child. So of course, the explanatory variable is going to be age, and the response variable will be height. So we're going to start by putting our data into Staplet. So let me show you what I'm talking about. When you go to Staplet, you are going to choose two quantitative variables because we are looking at an X and a Y. And then, of course, I'm going to type in my data. Now, I don't want to spend time typing in data on a video, so I've already got mine put in here. And this is what this would look like in Staplet. And then of course, when I begin analysis, I get my scatter plot. So I'm going to switch back to the notes, and right here on part A, sketch the scatter plot. So of course, you can clip it out of the Staplet page and paste it, or you can just freehand it like this. Notice that the X and the Y axis do not need to be labeled, but I clearly have the response variable and the explanatory variable with their units of measure. So you do need to include that. So working through this, I just want to talk through it with you. What is the correlation? Well, the correlation is how strong our relationship is. And where we get it on Staplet is right down here where it says calculate correlation. So I'm going to click on that. I get 0.994. What does that mean, Ms. Griggs? Well, the closer your correlation is to 1, or the closer it is to -1, the stronger their relationship. So if I'm using R and the scatter plot to describe the relationship, I'm going to look at my scatter plot. I see that it's roughly linear. Those points are pretty tightly packed there. And since R is close to 1, that means it's very strong. And of course, positive, it's trending in the positive direction, so that's where I get that. Notice that in my description, I include the strength, whether or not it's positive or negative, whether it's linear. In this case, it is linear. And I'm using my context, and I'm mentioning that there are no unusual features. Part C tells me to give and interpret the slope. So I'm going to show you where I got that. When I go back to Staplet, I'm going to click on this calculate least squares regression line because that is going to give me lots of information. So if you'll look down here in this box under regression models, we have our equation right here. And your equation is given to you in terms of X and Y, but we're going to write it in context. So the number that I got from this equation for the slope is 0.63497. And when I interpret that, I need to do it like this. As the age of Kalama children increases by 1 month. God, my writing is horrible. I can expect the height to increase by about 0.63 centimeters on average. Okay, so you can always interpret the slope this way. Notice that I have mentioned the explanatory variable first because as we move from left to right along the x-axis, doesn't X always increase? The explanatory variable always increases. So as the age, in this case of Kalama children, increases by 1 month, so I'm always talking about the explanatory variable increasing by 1 unit. what can I expect the response variable to do? I can expect the response variable, in this case height, to increase by about 0.63 centimeters on average, because that's my slope right there. And don't forget that on average part. Kids leave that off like it's not important, but here's what you have to remember. Is every Kalama child going to increase their height by 0.63 every month? No. It just means on average, that's what I can expect to see. All right, so give and interpret the y-intercept. This is part D. Here's my y-intercept. I got it from the same place in Staplet that I got the slope. I get it from the equation that is given to me. So remember, the y-intercept is the y value where the graph crosses the x-axis and is 0. So the way I would interpret that is I expect a Kalama child who is 0 months old to be about 64.9 centimeters tall. Guess what? On average. Neato. All right, so now we look at part E. We are to write the equation of the least squares regression line. Again, I got this from Staplet. The only difference is that now I am using my context of height and age in the appropriate portion of the equation. Notice that the slope goes with the age all the time. That's always going to happen. All right, the reason I use the word predicted instead of this little hat here is because when you're typing in answers on quizzes and tests, it's a lot easier to type in predicted than it is to find this little symbol. So that's what I'm going to have you do. All right, so on part F, we have to predict the height of a 32-month-old child. So I just use the equation from part E, I substitute 32 in for the age, and I do a simple calculator calculation. And I got approximately 85.25 centimeters. All right, so part G asks me for the coefficient of determination and to interpret its value. Well, I also got this value from Staplet. If you'll look down here in that same little table where the equation is over to the right, we have r squared at 0.989. So I am going to interpret that. I'm going to write it as a percentage. 98.9% of the variability in Kalama children's height can be explained by this linear model. Well, since the linear model has the explanatory variable of age and the response variable of height, it means that almost 99% of the variability in height is directly due to the age of the child. So that other 1% could be anything: nutrition, lifestyle, etc., etc. Okay, part H, we are sketching the residual plot and describing what it indicates about the relationship. So in the scatter plot, I'm going to go back to Staplet. In the scatter plot, you want to see something very linear, like you do. But in the residual plot, you want to see a nice scattering of points. You don't want to see a mathematical pattern. No parabola type patterns, no linear type patterns. So the residual graph here, I have just drawn by hand. And notice that the y values have taken on residual. Oh, man. Grr. Sorry. I'm not going to have a fit. All right, so the y values are now the residuals because they measure those vertical distances, but the x value stays the same at age. So how does this, how can we interpret this, and what does it indicate about our relationship? Well, since there's no pattern in the residual it appears that the linear model is a good fit for our data. So the linear model is a good indicator for the situation and the data that we've been given. All right, for part I, we're finding the residual of a Kalama child who is 23 months old. So this is just subtracting y hat from y. Well, the 79.7 came from right up here, all right? If I want the residual at 23 months old, the y value, the actual y in the ordered pair, is 79.7. And then this value of 79.5 comes from the regression equation. So you could type in or substitute in 23 into your equation on part E, and you could calculate it to get 79.5, or you could look at the residual and see that, well, I can't draw on this, but look at age 23 and look up in that dot, carry it over to the left, and it's lined up with about 0.2. So that is another way you can find the residual. Groovy.